Hey, this is Automat Live Coding, and today we are going to work on emitting machine code for our instruction cards. We have some test cases. I actually just published a devlog like a couple of minutes ago, which shows each of those small programs. And today we actually want to write our assembler object that will be able to store the state of all those instructions. Assembler objects are going to be slightly different. They are not going to use explicit connections to each of the instructions. Assembler is going to be a small object somewhere here that's just going to be used implicitly by all nearby instructions. So the connections between assembler and instructions, they're going to be totally invisible. Or maybe we'll show them somehow, but the point is there will be tons of instructions and usually a single assembler. There is no point drawing those connections. I can show the design for the assembler because we have it. Which one was that? I think this one. And there it is. So this is an older design, but it checks out. Can we hide this sidebar? I cannot. Anyway. And this is how it's going to look like. It's going to be a portal into a space where there will be checkerboards with register states shown. So here we will have lower byte and here the highest byte of each register. We are working in x86-64, so each register, at least each general purpose register, is 64-bit. Around the assembler, we are going to see a strip of Broadway lights showing the current, what the assembler is currently doing, whether it's paused, whether it's running, or whether it's finished. Here we'll have some buttons, though they don't have icons here, but they will have absolutely an Automat. And the icons are going to allow the user to pause and step through program. That's the plan. Below the assembler, we are going to see a hand pointing at the currently executing instruction. Yeah, that's it. Fairly straightforward, I think. And those things from here, we will use them directly as assets. For example, this hand, this texture here, we will, maybe I will not use them as like simple textures, but when we model the C++ code to draw this, we will use the effects, for instance, from this. Anyway. We will try to copy this style as precisely as we can, and we will try to do this in a vector way. So no raster graphics, we will try to avoid them, if possible. Well, this has to be raster. Okay, so how the structure of this code is going to look like. I think that when we have instructions, assembler is actually going to look around and find them from top to bottom. When we find an instruction like this one, we will just serialize it to memory, and we will serialize, if it's connected to another assembly instruction, it will be the next one in line. So this way we will emit all of the instructions in a consecutive block in memory. Eventually, the instructions will jump to something that's not part of the assembler world. Like here, this move CL10 instruction jumps into a timer. So for each connection which is not connected to an assembly instruction, we are going to generate an exit point, so that you can essentially exit from assembly at any kind of position. Like this instruction here, it has 2 exit points, because it has exit point right after the instruction, and it also has this jump, which also should exit somewhere, right? So we will generate a special exit point for this and for this. We don't have any sort of exit points in our current code, so this is something new that we will have to add today. And we will also have to add this serialization loop, where we, in assembler, we look around, we find all of the assembly instructions around, and we dump them to memory one after the other. There is something that instructions currently have and I don't want them to have, and it's the addressing memory. So if we look at library instruction, this is our instruction object. Each instruction contains a size and an address. This is very strange, because this is redundant with the mcinst object, which is like a generic LLVM way of representing instructions. It's fairly large, but there is no point storing this size anywhere. And the address, I want instructions to be reusable in multiple different contexts. So here we are using instructions to actually build something, right? We are building a new code out of instruction objects. But if you think about, for example, analyzing the game memory or the game code, I think there it would be nice to have instructions that represent foreign code, code that we often cannot edit. That's read-only for us. And this is mostly fine. I mean, we theoretically also store this address, but I think it would be more natural if there is, if each instruction belongs to some other object, the object which actually owns it, quote unquote. And this, in our case, is going to be the assembler. Yep. If we want to analyze code from, for instance, like an external program, then we will have another object which is going to be hooking into memory of the external program to read its code, and it's going to own the instructions. Anyway, let's look at what we can do right away. Okay, so our assembler object is actually not it's not in the library, but I don't think it has to be, really. Or maybe it should be. So the thing is, there is no point to have an assembler object if you don't have any instructions. I think instruction could create an assembler. This could be like it currently does. This kind of object that is being automatically created whenever an instruction executes. So what happens when we run the instruction? Sorry, is there any code that I did not submit? Okay, so here I had this find or create assembler, which we don't need. I mean, we will need it, we will restore it. Okay. Let's hide this div. Or maybe let me take a quick peek. Boring stuff. I don't care about those things. So let's make sure that when we run an instruction, it creates a new assembler object. I think we used to have a run here. This is our prototype. Oh, there is on run. Okay, so inside assembler, we will define a new argument type. We should define this as an extern. Okay, we should put this in a different namespace, I think. Okay, so this connection is configured to connect to multiple instructions, to all of the instructions around, because it has autoconnect radius infinity. We have a style here. We have two styles of connections now. We will add more. Maybe this would require extra style like hidden connection, something like that. Okay, so this is the first thing we need. I think it would be nice to also put this into library namespace. Okay, now So we have some functions inside argument that allow us to follow the links. In this case, when an instruction is executed, it really needs to find its owner. I think we'll need to add a new function here in the argument. We need to add this to header. It's hard for me to come up with a reasonable API for arguments. So the point of arguments is to actually provide those helper functions for navigating the graph of objects. Here is some new API. Okay, this is just a helper for another method that provides a config. So we'll have reverse find config, yep. It's going to be similar to regular find object.
Knight says,
Hey everyone.
Hi, Knight. Okay, and now we need this reverse find location function. when I actually look at this, maybe in find config I could specify different parameters. So let me try that. So instead of adding, like, duplicating the number of methods that we have here, we'll just have a new field in the find config that will tell us that, hey, we want to find something in reverse. How are we using this search radius? Okay, we're actually not using this at all. This is not used anywhere. Overrides autoconnect radius, I don't see it. Okay, if we are not using it, I can remove it. It should still work. So I have a plan for next week. If we manage to get assembler to work, next week I actually have some issues in GTA 5, like money issues. I found there is a glitch to make money in GTA 5, but it requires repeating the same action over and over, sometimes multiple times. So we are going to try this. We are going to try to create a macro that will run this glitch for us. It's kind of tricky, so I think macro is going to be good at it because it's fairly repeatable. We'll see. Okay, Automat is working. So let's handle the new direction. maybe I can store this as a boolean. Connection is explicit, then okay, here we also should change this. Okay, so if we didn't find any result, and we want to create a new object from prototype, which is what we want. Ask the current location for the prototype of this object. Nice. So we have to ask the object what's the prototype that's going to be used to create a new instance of a new object for this argument. But the thing is, we are trying to follow the connection in reverse. So this connection is actually used to instructions, yeah. Maybe, actually the initial version was nice. Maybe the connection should go from instruction to the instruction owner. Yeah. That might make more sense, I think. Okay, that's good. That's good because that means we are not going to need this.
It would be great if you streamed about other activities besides coding. It could be nice to watch you working on Arduino kits live, or maybe doing puzzles or a vlog-style stream.
I think about this. So I'm not, for instance, I'm not playing any games on stream because I'm not just very good at it. I think part of the thing that's fun about watching people stream stuff is when they have some experience doing this. Like, this is why I like speedruns, this is why I like all sorts of challenge runs in games. And yeah, I don't really think I'm that good at embedded development, for instance. But I will consider this, yeah. But we will need this arc prototype. Okay, I think this code will actually work pretty nicely. I think I should be able to, for instance, set CX to 10. Or not. Let's try to follow with debugger whatever is happening here.
There was another streamer I used to follow who did coin-related streams. At other times, they played games. But you could still see the coin trades in a corner of the screen. Speedrunning could be great. You could start with Detroit, Become Human or Max Payne 2 as a test stream. Speedrunning could be great. You could start with Detroit, Become Human or Max Payne 2 as a test stream.
I will consider this. So it's popular. It's a good strategy for getting lots of viewers on Twitch. I see that some people use this. The thing is, I'm not sure if it's a good kind of plan. Because it's going to... I would like to attract mostly coders, mostly programmers. And I think if I start playing games, it will definitely kind of bring more people to the stream, but that's not the goal, that's not the point. So I would also like to have a fairly... I'm picky about the audience, right? And maybe there are some games I'm good at, so maybe, I don't know, maybe we could try those. If anything, I would probably play them with Automat, so like cheating in those games. Okay, that was this annoying bug. I have no idea what this is. Again, it failed again. will have to fix this. Okay, now we should be able to do the debugging. Should work now. Okay, so we are here. Let's follow this. So our assembler object, this should have a pointer to machine code. Yep, it has. And register state, which it also has here. And the list of instructions, which is empty. Yeah. We are not updating those addresses. So there is something that I used to do, which I am not doing anymore, which is causing this issue. So I think assembler used to have, sorry, no, instruction used to have on connection added or something like that. Connection added. I think this is where we should put a breakpoint. Let's try again. Now I will run this, and we crashed. What has happened here? Okay, the persistent image is definitely mapped to some address. Yeah, I think the issue must have happened in a different thread. Because this one was just drawing stuff. Or no. Image is empty. Huh. Very, very strange.
I see. So in this scenario, people who come for the gaming streams will also end up watching your programming streams. Then, one of two things will happen. Either they'll get inspired by you and start learning programming, or they'll pressure you to do more gaming streams.
Actually, this is not what I was thinking about. I was mostly thinking about the audience shifting. Because Twitch and game streams, they have a very particular kind of, it's a very distinctive culture, which I don't particularly like. You know, people on chat stream, like constantly sending emotes, like random messages. I really prefer those like longer messages, which allow me to discuss stuff or chat with people like really, and instead of those very short barks that Twitch I think encourages. Yeah, to keep like the kind of some kind of chat culture kind of in check. So this is what I was thinking mostly. I don't mind like having more people. It's just I think growth is good as long as it's not too fast. You've probably seen this situation many times where new people come to stream and just start sending like tons of random messages. Because this is how streaming usually works. It's trying to be engaging as much as possible. It's trying to create a show. This stuff here, to me, is just so weird. it is not possible that this object has no image value. Hey. This stuff should absolutely work. Interesting. I usually use the Google passwords to check my passwords. I see some of them have leaked. So my Instagram password, for instance, has leaked. The problem is I cannot log into Instagram because they have some bug. I'm just blocking right after trying to log in. So I hope whoever compromises my account fixes this issue. Okay, I wanted to look at this other thread. So we are running some code. We are in run machine code. Specifically here. I have no idea how this could happen. Attempt to draw an uninitialized persistent image. This breaks all of my assumptions. Yeah, breaches happen. This is just a fact of life. There is a nice way to log in, which I always wanted to see, and this is using personal ID cards. You know, in US those would be driving licenses, but in many other countries there are like ID cards. They often have chip inside them, and that chip can often do cryptography operations. And it can be read by a phone, so by tapping an ID on the phone, you could sign in. It's not widely supported, it's very different from country to country, but it could work. And as more countries implement this kind of stuff, it will be nice because it doesn't require any passwords. It only requires a physical token, which is your ID card. And some phones can actually even copy this. So it's possible to maybe not copy an ID, but there are like, my country for instance has a government app that can move an ID from a plastic ID onto a phone. They do some like crypto magic to make it work. Okay, I am going to just restart the execution. I have no idea why we have this initialization error here. Totally crazy to me. I will still log the message, I will just not crash the program now. Yeah. So this kind of sign-in system, it would have to be, it would have to offer some sort of anonymity also. Okay, let's go back to here. Let's create a connection. Now let's run it. And we get segmentation fault. Address not mapped to an object. I think it's just wrong thread. Or not. So weird. What is happening here? Okay, but here again we have a wait instruction. So I think this machine code loading, this must be messing something up. Oh, actually, I think I have an idea. I think I know why. I think when we allocate machine code, the allocation may be failing, but we are not using like the proper address where the memory was allocated. That's one option. See, here we have machine code at address crazy high. I mean, we're still entering this entry point at fairly wrong address. Okay, I will fix this. I will take a short break, make some tea, and be right back.
Lucarip says.
Keep viewers on streamboo.com remove the space 89's 3BFC.
Yeah, interesting times. I'm still waiting for the first quantum-based attack against anything, really. I don't know how high the numbers can be factorized using quantum computers right now. So quantum computers can only do some specific, they can only break some algorithms. There is tons of types of encryption that are totally resilient against it. I'm not sure. I think people say that elliptic crypto is not resilient against quantum attacks. If I remember correctly, it used to be, but maybe I'm remembering stuff wrong. I've seen people saying that, hey, elliptics is not good enough. Yeah, I'm not in the field, so I'm not up to date. But there are ways to encrypt stuff using shuffling and tables, like similar to what AES is doing. Symmetric crypto is totally safe. Yeah, what you're saying is actually a very key kind of thing that's used in anti-abuse for fighting bots and botnets. Sorry, botnets and abusers. For them, the calculation is often economical, so they have some investment and they make some money out of this. For example, when they create fake accounts, when they spam online. So it's only about making it not profitable to do this, and then people stop. I am removing address and size from instruction. It's going to break a lot of stuff. But it will also fix some things. I don't know it. I heard the name Marvel Rivals. Looks a lot like Fortnite. Nice. Good one. So it's a it's a very quickly and haphazardly coded game, I see. Oh, this is actually doable. There are tons of ways to get on a local network. It's not a very great security boundary, local network. I use it a little bit, but there are ways to get around this. So your website extensions, for instance, they are on your local network. Any apps on your phone are on your local network. Yeah. And there are like malware distribution services which you can literally pay, and they will run your code on local networks of other people. It's nice. I'm not super interested in Marvel Rivals. It's not my kind of game. Args, yes, this is what I forgot. So an object needs to say what arguments it expects, and only then it's going to be used. So here we have this run machine code, or maybe update machine code. or we're emitting all the code. So we are filling our machine code with NOP instruction, so it shouldn't do anything. We have a fixed buffer of code, 4000. It's fine. Do I like hero shooters? I don't think so. I'm not a big fan of shooters. Maybe some of the games I like are shooters. Recently I'm playing GTA. GTA is kind of a shooter. But it's a very particular kind of shooter. It's a sandbox, mostly. Shooting is actually kind of optional in this game. Not entirely, but you can, if you don't like it, you can do lots of different stuff in GTA. Lots of fetch quests. I actually wonder, where do we use these instructions? Okay. We have connection added and connection removed, which adds the instructions. Okay, so we are going to do basically the same thing we are doing now, except when we iterate over instructions, okay, we are not going to set an address or size for each of them, at least not within the instruction. It would be nice if we could fill this within the connection, but I don't think connections in Automat allow us to store any data. No, they are very simple data structures. Maybe we should store stuff inside those connections. Yeah, they are really milking the Elden Ring with DLCs now. Rightfully so. It was very well made. It has tons of annoying things, but... So I played Black Myth Wukong and Elden Ring, and my experience from Black Myth Wukong was that like the amount of just bugs, really bugs, was so frustrating. It's a very reflex-based game, and they have this issue where when you are attacked, sometimes the game will lag. So you kind of have to fight with a boss for a little bit so that it attacks you using every attack, so that it compiles the shaders before you can actually start fighting it for real, so that it doesn't lag when it attacks you. Maybe it's less of an issue if you have a fast CPU. Nope. I think instead of storing those instructions here, I should probably use the connections to iterate over them. Okay, let's take it a step at a time. Let's start working with code emitting, update machine code section. So instead of just iterating over instructions, yeah, we need to do this. And we need to come up with some ways of doing the exit points. Because each exit point has to be unique. Maybe we will push something onto this stack and jump. But the stack is not reliable. So if the user uses the stack for anything, that would be annoying. I will have to think about how we can save the exit point position. Yeah, possibly. So, in US there are those groups that are doing historical reconstructions of battles. There are quite a bit of those around here. So I guess US has the kind of US... I don't remember what was it called? US Civil War? Yeah. American Civil War. So there is a lot of people that are doing reconstruction for this. In Europe we have people who are doing reconstructions for the medieval kind of battles. So yeah, naturally they are good at it. Yeah. When I was in high school, I was actually attending one of those groups. I actually even got cut a little bit in the hand because, yeah, we haven't been super careful when doing the fights. It was like mostly role-playing stuff. It wasn't really like proper historical reconstructions. I had a friend who was kind of collecting the swords. I mean, he had some authentic ones and some of the replicas. And we used the replicas to fight sometimes. I don't think sword fighting is a popular sport in the US. Yeah. It wasn't exactly Germany. It's much more complex than that. It was a battle against Templars, the ones that you are not Templars, Teutons. This was more of a like religious. Maybe country is a wrong name. It was more like an order of knights that used to control a very large territory. Oh, it wasn't a religious war, that one. Both sides were Catholic, I think. Teutons and Poland and Lithuania, everybody was Catholic. That was like Dark Ages, right? Almost all of Europe was Catholic. Okay, I am going to remove this instruction set from assembler because to emit basic blocks I need to follow the next instruction, and for next instruction I don't really have any reasonable hooks. So I think this code here, it will just have to traverse a bunch of connections. Yeah, I am just getting rid of this. Now, what do we want to do? Okay, so this is a pointer to the location object. And this is an array, a multiset containing connections. So I guess I can call this equal range. Yeah, to do this, I will need some more stuff exposed. So this argument, assembler arg, it has to be exposed. Cool. And I think that should return pair of iterators. Battle of Nations, let's check this out. Nice. I imagine it's a fairly contact-heavy sport. Okay, so what I want to do here is I want to get all of the instructions which are connected to the assembler. And I'm not going to do any of this. So this will give me a list of connections. I think I will put inside connection the ability to store custom data. It must be, I think it must happen. So it's all of the graph databases. If you're into databases, they use triplet stores to to encode the connections between objects. And this data structure triplet, a set of triplets, like a list of triplets. This is probably the most general data structure. It allows you to link anything to anything. It allows you to create relations between relations and relations between them. So it's very... in addition to expressing very direct connections, object to object, it also has the ability to express higher order relations. But because it's so powerful, it's also very complex. I mean, not in usage, because the data format is very simple. It's just a list of each element is a list of 3 pointers. But there are just so many ways to encode just about anything that it's hard to work with. For me, it causes this kind of design paralysis where I have no idea how to design even the simplest model in this paradigm. So I'm not a big fan of it, but I do recognize the power of this representation. So I think if we want to make Automat slightly more general, we will have to store something inside connections, and I think this something will be maybe some extra objects, something like that. So there will be something like unique PTR object. Right, so each connection will be able to hold something inside. And we could even get rid of this pointer behavior once we do this. Yeah. We will not even make it any larger if we change it. Or this argument. Yeah, we could also change the argument. I see some interesting options to refactor this. But okay, back to the Earth. Let's create a list of those instructions. So for each instruction, we'll have the instruction itself. Yeah, let's also record connection. And let's also record position, because position is actually going to be important for sorting those instructions around. Okay, so this is our list of instructions. And we will actually do this slightly differently. So we will have this vector. This makes sense. This is very good. This is how it should be. But instead of just iterating through this vector, we will have a search, like a graph search. So we will create a set of visited instructions. And a queue of instructions to visit. And actually, I think before we do that, we should figure out how are we going to actually store the exit point. So there are a bunch of, let's look at what instructions do we have here. We have move. So we can move a register to some address in memory. I actually don't want that. I would like to set some address in memory to some value. Let me run Automat, because it's actually convenient for browsing instructions. So we have this set instruction. I'm afraid there may be no instructions that take a fixed, like a full 64-bit address, because this is what I would like the most here. I remember there was this one. Let's see if it has any other variants. So this is one. What arguments does it have? Okay, so it has some address in memory. And that's it. It should have more, right? Yep. It's a very interesting way of looking at this. What you say? Because the countries used to be very, very different in the past. It's hard to say even that they are the same countries. I'm looking for uses. Okay. How can I store the exit point? So every exit point, the way I see it, would require this. Then this. And then I would then only after I save some registers, only then I would be able to set some exit value. Not great. I think we'll just use stack. Yeah, just use a stack. So each exit position will be numbered. We will use small numbers. I'm sure there is some push. Push something immediate. Yeah, and there is this push 16i. Yeah, this is what we are going to use. Push 16i. Actually, what the red eye do? Okay, I see. I'm using this ret64 to jump into the code. I think I will have to store the address of each instruction. I actually wonder. Okay, we will change this. So instead of emitting unconditional jump, okay, this is what we'll do. If so what we want to do here, we want to emit this instruction at the current position. Let's say we have a kind of cursor inside our machine code. Okay, so we are emitting this into these code bytes, yep. Okay, it says fix-ups not supported. It's not going to be true. I mean, we will clear these fix-ups, but we kind of just have to record where the fix-up will point to. So there are like two connections that we can have. There is the jump, which jumps somewhere, and there is the next instruction. Next instruction should always be just serialized right afterwards. So those fix-ups, I think we have to save them. We will have an offset for each fix-up and an instruction, which may be set to 0. So we will call this machine code fix-up, machine code fix-ups to distinguish them from the code bytes. Let's call this instruction bytes and instruction fix-ups to distinguish those two. And honestly, all of the instructions that we have only just one fix-up at most. I can actually call this set offset here. But I don't think it's going to change anything. The way I saw this, I have to kind of manually edit instruction bytes. actually set offset is something totally different. We want to have a value. Or maybe it should be the place after the last byte of fix-up, because this is also the origin where the fix-up should start from. I'm not sure if it's a good idea to use the same variable for both. But in x86 this is how it is, so okay, I am not going to do any of this right now. No jump instructions here. So it's possible that this address will be somewhere in the middle of the instruction, but I don't think it's the case right now. Okay, and here we have to specify the target instruction, which may be nothing. So here we should grab the location. So here we should store the that's fine. Okay, this clearing is probably unnecessary. This is such an awful way to write this code, but I guess for the first draft it's good enough. Okay, pretty much here. Yeah, here we will have to generate an exit point. So I think as the code, as we are emitting like a run of code, it will be a continuous run. We have to kind of collect all of those exit points. Yeah, we just have to collect them. And then after we after we finish the run of code, for each exit point we will generate a section that will actually do the exit. Otherwise, okay, and this will do dynamic cast, so there is that. Actually, we can even actually, this is not next instructions, this is jump instruction. Now that we are here, instead of starting the next iteration of this loop, what we really should do is we should grab the next argument and do this. Something like that. I think we can group those pieces of code into small lambda functions. So in order to emit instruction, we need several things. We need a location. We need an instruction. And that's pretty much it. So let's copy this code and see. If this would work. Load it entry.lock. We have lock. This could be way smaller. Oh, way smaller. Let's make it 32 bytes. So this function, this lambda, has a side effect. It emits the fix-ups into this machine code fix-ups array. Some of them have null values, some of them don't. I think the jump instruction jump instruction may be implicit here in this model. So if we want to jump, right, an instruction has a fix-up. And then instead of doing this whole fix-up, we could just serialize the code just one after the other. So the jump is kind of unnecessary in our model. It doesn't hurt if we have it, but we also need to implement jumps implicitly. This is actually interesting. So when we have args, right, this, I will clean this up in a moment. So if we have a jump, then we should not call the next. Yeah, so essentially the jump instruction is not going to have the next connection at all. So you cannot connect it straight. You have to connect it using this jump argument. This will be interesting. Actually, it looks like it's compiling, so let's see if this works. If we just remove the next connection from jump. Yep, it only has the side connection now. And the others, they have 2 exits. Cool. So we are going through our instructions. We are checking if they have been emitted or not. If the instruction was already emitted, then we are just skipping it, right? There is no point to emit instruction multiple times. But here we should follow the chain of next instructions, kind of. Let's also pass this as a reference, because it's required. So the point is here we are emitting the whole sequence, the whole chain of instructions following the next argument. So we are grabbing the next. Next argument. So if the next instruction is empty, if it exits the world of assembler, then we need to do this. Then we need to emit our fake jump. And this terminates pretty much the basic block. Short break, or actually maybe not so short. I will grab some food, so break until 2:20. Should be good. So, see you soon. Hey. Yeah. What's up? Okay, I think here we could just put break. Here we will do the exit point. Okay, I can change this to while inst. Actually, the exit point is going to be fairly straightforward. It's going to be pretty much this. Let's just call this jump to epilogue. But in addition to this jump, we will also have a push. Is push 16i. Blah blah blah, we are emitting this stuff to instruction bytes. We should also copy the instruction bytes into our machine code buffer.
Keanu Farrow says,
Hey bro, do you use Linux?
What's your guess? I mean, when you see stuff like that, does this often happen on Windows? Actually, check this out. We have push 16i8. Here we will have a counter.
Been still on Windows 10 since 2017, and I think I need to switch to Linux, as nothing ever lasts forever.
Yeah. The speed is nice. Like after you switch, this is the first thing you notice. It's that the old hardware that you had suddenly becomes faster. Because it's not doing, I guess, crazy things that Windows is doing in the background. I have, for instance, this thing with this antivirus scanner, Windows Defender. It's messing up the performance of the laptop so much. I really want to disable this. It's just hard. Windows doesn't let me.
Maybe I will be a DigaChat assembly programmer who uses Vim and drinks too much coffee soon.
Yeah, it may happen, especially if you're going into a university. It tends to change people. Or actually, instead of pushing the exit find count, I could push the RIP register. Yeah, we are just pushing this register just before the jump. Let me see. Online assembler, yeah. It's a 1-byte instruction. It's perfect. It's absolutely perfect. Oh, actually no, not RDI, RIP. Unfortunate. But you cannot do it. But there is a call instruction. This. Let's see what kind of calls do we have. Actually, we can check here, I think. Yeah, I forgot about the obvious. We have the call instruction, which allows us to do this, what we want. I wonder what's the thing we've called 64. Okay. 32-bit displacement extended to 64 bits in 64-bit mode. Exactly what we want. We can also give her an address in a register, but we don't want to do that. Yeah, okay, I think this is good. So each exit point is just a call instruction, I guess about 5 bytes, something like that probably, maybe 6. Nice. So there is probably a different way to do this, where I would like emit sections of code and then kind of decide if I can lay out them properly. But I don't think it's necessary. In Automat we are going to work with tiny pieces of code and I'm just emitting them in order, from top to bottom pretty much. So we will do this emit exit point, but I will also do the fix up. This offset is actually the cursor where we are writing. Let's already fix up and here. And let's store the target offset as an absolute value. Exactly. What's with our machine code? What is machine code? What type is it? This is a unique pointer. I will just cast everything to signed so that the compiler does the proper subtraction. Honestly, it doesn't matter. The subtract is identical. Okay, here. I don't think I need jump base. Cool. So I am taking the call, emitting it, and calling fixup for immediately. Okay, so after I do this, I should wait, instead of advancing fixup I should remove this fixup. Yeah, and continue with others. All right. Or actually, this type of removal is actually a little bit problematic. There is this erase index I could use. This doesn't seem right. Okay, this we can get rid of completely. When it comes to instruction addresses, I think it would be convenient if we had this for a little longer while. Now this is going to be interesting. So when it's possible that we will have multiple instructions pointing at the same one, which is already somewhere in a memory. I think one thing we should do when we have those instructions would be to clear their addresses so that we don't need the visited. I think I should kind of sort those instructions here, because some of them have this next pointer, pref pointer. Anyway, let's say I start from a random instruction and I'm emitting them like one after the other. Eventually, this loop will find an instruction that already has an address. I think this memcopy, I could do it later. Or not. I will just get this to work now. I will clean this code later. Jump target is going to be instruction address. I could probably have a function for this.
"92 UForb just followed on Twitch."
Hey, thanks for the follow. The interesting thing is that those exit points are just, each of them is a call instruction. So after a long run of machine code, we'll just have a long sequence of calls at the end, if there are many conditions there. I guess that's fine. Okay, address. We are setting it here. I think this is the only place where we emit an instruction. This is good, we can get rid of it. I think that should be it. We probably have to handle the 1 byte fix-ups. So Let's see, when I emit an instruction, oh yeah, we forgot to emit the, to do all of those fix-ups. Okay, so I think here we should check if we resolved all of the fix-ups and send a warning if we didn't. This will break out of this while, okay, but we'll continue here. Okay, we also have to change the epilogue, because our epilogue has now an extra bit of code, not code, an extra element on the stack appeared. We have to clear it. Okay, our machine code, how do we execute it? Okay, this is a void function. I think we could turn this into this. So now we expect an exit value. I guess it will be faster to ask LLM. This is a basic thing, so LLM will know this. I suspect it's rex. This will be rex. Cool. I'm giving it 90% probability of crashing. I mean, we don't even support one byte fix-ups, so those operations will certainly fail. But I guess I could try running this. Right, it should set the register to some value. Nope, not really. Hey, that's interesting. We exceeded the size of small vector. Epilogue, prologue should be fine. Those are tiny instructions. This should also be fine. I mean jump, yeah. I have no idea. Let's run debugger.
Quack Pep Zero says,
Epilogue, prologue.
I'm doing it in a very weird way. I probably should do it differently. So I'm first emitting. So our block of machine code actually has user functions, like user blocks of code at the start. Then there is a sequence of knobs. Then there is an epilogue, and then there is prologue. So prologue is at the very end of this block of code that we are creating. The CPU doesn't care, so it's not... oh, come on. Yeah, so it's not causing any issues. But typically the prologue is at the start. I think it makes function layout simpler if the function starts with the prologue. Now I can see the stack trace. So nice. It's so nice to see that the segmentation faults are coming from the right thread now. At least we have that working fine. Index is 0. What? And size is also 0. How? Oh yeah, I see. Okay, yeah. Okay, that should be enough. Another attempt. Cool. Yep, we need debugger again. how is this happening? Fix up and equal to.
What's fix-up?
So fix-up is the internal name for a relocation. Internally, LLVM calls relocations fix-ups. It's something that they just are leaving in memory, and then after code is fully emitted, they fix it up with correct address. It's kind of like compiler time relocation. Kind of.
I see.
So we have all of those instructions. I see. So the issue is that some of the fix-ups that we have, we actually do have some instructions that have 1 byte relocations. So we need to support this. Otherwise it's just going to keep crashing.
What's 1 byte relock?
They are actually the most common relocations. Or fix-ups maybe. It's the better name. This, when you have a jump and an 8-bit offset, this is essentially what's one byte relocation. It allows you to jump for a very, very short range, like usually less than 20 instructions. Or something about 20 instructions. But it depends. If the instructions are very short, the range of this jump is actually longer. And the way that LLVM does this is they assume that all of the jumps will require this version 32-bit address, like 32-bit displacement. But if the displacement is small enough, they are replacing those jumps with shorter jumps. It saves 3 bytes. It would be nice if x86 actually used variable length integers for those things. It would make it even more messy, but also it would simplify some things. It's already messy, right?
Thanks.
What happened here?
CP Chica says,
I was about to comment that none should ever use GMP, but then I remembered that JJAL commands are risk-based.
Oh, I have no clue about how risk works. Sorry, not risk, risk V. Like risk in general is like this whole category, but risk V is a very specific architecture. And I hear a lot about it all the time. One of my favorite channels on YouTube kind of keeps bringing this up.
Risk generally links jumps, same way return does in 8664 or...
I like how the TTS pronounces this. So you push it to some stack and then jump to the value from the stack or from some register. I think I messed up something with parentheses. Yep. Oh god, this is what LLMs do with the code. You kind of hit tab accidentally, and in addition to fixing the one thing you wanted to fix, it also decides to delete some important code later. And I have no clue if there was actually something more than the close brace here. Okay. Let's hope there wasn't. So those fix-ups, they are not proper functions, they are lambdas, so I cannot really take address of them. But that's fine.
Depending on the risk implementation, it behaves differently. I know for a fact that custom-built RISC-of CPU for hypercontrollers usually increment stack pointer by X, then perform jump do some stuff, and then when they are done, jump to address X.
Okay, look what happened. We have this spider connection now. This is the assembler. It connects to pretty much all instructions that we have because it kind of manages them. And here the current visualization just prints the value of the array X register. I could probably mess with it a little bit and increment it like that, and we should see. Okay, I need to zoom in and zoom.
Right there.
Yeah, this is why I want to have implicit connections. I mean, it increments. So executing one instruction works. Can we do more? Okay, so this would be very interesting. I think we have code to actually make this work. This should just cause infinite loop. So we will emit code if the next instruction already has an address, we will emit a jump. So that would create an infinite loop. Yeah, okay, it worked, nice. I will turn down the volume.
Coacapzero says,
Why the sound?
Good question. I think when we execute the next object, we emit a beep. So maybe this is what happened here. Okay, I want to have this increment instruction. I want this in a loop. So let's start it up. Okay, now it crashed.
TP Chica says,
Why not?
It almost worked. So I try to get the next. I can resume the music. So I can get the next instruction, and this instruction will already have an address. So we will instead emit a jump. Back. And I think here so I think when we emit this jump we don't need an exit point here. So that's one thing. So that was the first assembly loop that we created. It worked once. Let me try first running this. Okay, this just works, no issues. I can try now with this. it does increment the value, and now I will create a loop, again lowering the volume. Operation not permitted. Interesting. Oh, I know. We are spawning multiple threads now. Yeah. Because there are like two... So the counter is still incrementing, right? It's FC now. But if I open btop, you'll see that we have a ton of threads. Okay, this crashed. Okay. And the issue was that our instruction, when we execute it, it goes into run machine code, and then it returns null pointer from here. And that means that it immediately finished execution and the next instruction should continue. Basically. I honestly don't know how to fix that, because this is kind of deeply within how we run stuff. So whenever we run any object, we call the onRun function, and when we don't return anything, and here we run this in another thread, so we immediately call done running, and we schedule next. Okay, so this is the next sound that was playing, that was causing the issue. Okay, I think we could return this long-running interface. So how does it work? We'll have to do something interesting here, because let's say we have something like that. So the user runs this instruction, and there is actually going to be a chain of other instructions that may be... So we have this assembler object. It's going to track whatever instruction is currently running. We can inspect the instruction pointer from another thread. So this assembler is actually going to have to dynamically manage which instruction it's currently working on. Needs to implement the cancel. That should work. Yeah, cool. So this will be the job of assembler, to actually clear the long-running state from other instructions when they finish execution. Let's run everything again. Okay, the CPU is fairly chill right now. It's not doing anything special. Let's try to do this. Right, so this creates our assembler. Now I can try to increment this. That should just work. Yeah, we incremented a number. Cool. And now the loop. Is it looping? It doesn't seem so. I don't see any CPU which would be busy right now. Unfortunately, it doesn't seem to work. But okay, I want to print the machine code that we have emitted to see if it makes sense. We had here Okay. This is quite a bit of code. We're probably calling this function a little bit too many times. So I am first printing the machine code string and then epilogue. So the shorter one is actually the machine code and the longer one is the epilogue. Let's try to print them now. Or disassemble them. This one was much better in my experience. And I think this roughly matches to the instructions that we had. So we have the move the L A, right? This is this instruction. B2 away. And then there is a call to something, to one of the exit points. Yeah, this is just our exit point. And then we have move CLA. Yep, this is this instruction here. And then we are calling the exit point. Nice. Okay, and it takes just 5 bytes to exit from assembly. And then we have this loop instruction, which I guess it's this one. C205. So this is something that will jump over the next 5 instructions. So this will go here. So this connector here is actually serialized here into assembly. And the next, this connector here is here. Then we have decrement and JAE, FECA, yep, and 7305. So this jump goes here. And this one is this connection here. And then we have increment. Increment, compare, C3 away, yep, and jump below to some address. Actually, this is kind of strange because it says 0x37. I actually wonder how those fix-ups are encoded here. Maybe the encoding of those fix-ups is actually not so straightforward. Oh, no. Yeah. It's printed here differently. The disassembler uses absolute values. So it says that, hey, we are going to jump here. It's good. Nice. And the last kind of instruction is this set AL0, which is almost at the very end. Cool. Our machine code, it seems perfect, actually. Let me take a look at the prologue epilogue. It's mostly unchanged. Okay, so this is the epilogue. So we are taking array X, saving it somewhere in memory at this address, whatever this is.
92 UO45 says.
Please tell me the name of the track.
It's on the bottom of the screen and it's downloadable. So if you go to liveautomat.org, music tab, you can download those tracks. FYI, this is AI generated music.
The X.
Okay, so this is our epilogue. We are just restoring values of some registers. Or sorry, not restoring, saving them. And then we take the return address from this stack and we put it in array X. And we also restore some of the registers also from this stack. And then return. And here is a prologue. Actually, the final part of our code is the prologue. We are pushing stuff in reverse order. Yep. All correct. We are also pushing RDI, but this is because RDI contains the address that we actually want to call, that we want to jump to. And we are going to jump into this address using the return instruction. We are doing it this way because we want to preserve as many registers as we can. Yeah, and this is them. Okay, so now we could probably loop. I will delete some of this stuff, we don't need it. I just want to see if we can create a proper loop. So this is our machine code that we created. Let's see how it looks. So we have increment and then jump. And this jump is not looking good. Huh. It is looking totally wrong, actually. We don't want address. Address is absolute. We want offset. Now this could be an infinite loop. I really need to create ways of deleting stuff in bulk fast. What is going to happen? It doesn't look great. The jump feels a little bit better. Yeah, we have an infinite loop now. Definitely. So we don't see anything here. I wonder why. So Automat, theoretically, it should use 100% of the CPU now. Yep. So I guess it is looping, but we are not reading it. Maybe we just didn't implement this. Yeah, I think that's the case. So it is actually, so we actually have a thread right now, which is just incrementing this register over and over. We just need to read the contents of the memory. I am kind of happy with where we are, so let's commit this. And we can remove the to-dos. Okay, I guess it would be nice if we periodically checked the contents of registers. So now we've called this ptrace, so at this wait for child to exit. Or actually, maybe we can do it differently. So when the machine code is running, we could just record in the assembler object that, hey, it is running. And whenever we have a frame that we want to render, this is when we will call ptrace to pause the thread. And this wait pid, I think we will not wait here. Okay, I'll make a short break and soon we will continue. All right. So when we run machine code, we really shouldn't expect it to finish anytime soon. Look at that, we even have a separate stack for the new thread. Okay, there is one thing I want to see. I want to run this in debug mode. And I want to pause the debugger, and I want to see how does the stack of the extra thread look like? It should be completely empty, I think. To delete almost everything. So this should create a loop, which now should execute. And now this is the TID of the thread that we started. Oh, it's not part of the debugger. But how? Yeah, our extra thread keeps running. Even when Automat is paused. Here we are waiting until the child thread finishes. It's not going to finish ever. So we can just stop it. Let me see how to use ptrace to read the registers. We have this peak user. I have no idea what is the user area. Sys user age. I mean, this is exactly what we want. It contains all of the registers. We have RIP, so this tells us where the instruction is currently. Okay, I think to execute anything, we have to first pause the Tracy. There should be something to interrupt. Yeah. Okay, so now the cool stuff begins. So inside the assembler, we can store, by the way, it's tiny, it's 72 bytes, this whole assembler object. We have this regs structure. I think we need it, yeah. We have this text. So when we execute this text, what we could actually do get rid of those things. Okay, this is just an integer. I think this is the only PID that we really have to deal here, so we can just maybe call this PID. And if it keeps executing, then I think we need to... Oh yeah, it's going to crash on Windows. We don't need such large stacks here. Actually, I wanted to see if I can use C++ thread, because C++ threads they might be more cross-platform than doing everything directly. Okay, I think we might not need this. Let's see if this will still work. Okay, seems like we don't need it. Okay, I think our thread, this thread arg, will need to contain TID. So when our thread executes, we will set it. And notify. Okay, so this way we know what is the TID. I hope it will work. Let's see if it works. It doesn't look promising, honestly. Well, it kind of worked. I mean, I cannot seem to run this again. This is probably because of the long running. Okay. Yeah, it looks like this ptrace sys is working. So now that we are not actually spawning a separate process, we are just spawning a separate thread, we have shared memory, we don't need stack. It's nice. Or no, a separate thread gets a separate stack automatically. But we can run debugger, and now when I create an infinite loop and pause the debugger, I should be able to see the assembly thread. I could even put something here to change the thread name when it starts. Okay. It is computing some stuff, but not too much. You guys go away. Now I can run this. Right. The CPU jumped to 100% because now we have a thread that it jumps between cores, but we have a thread which actually increments AL in a loop. Now I should be able to pause, and this thread should be somewhere here now. Maybe here. Yeah, it's here. Look, the stack is completely empty. It's just this. So we can execute one step. I mean, this is the interesting one. Okay, so now we can see that it has increment byte AL, so it increments 1 byte and then jumps back here. Yeah, this is the same address, it's just lowercase here. Infinite loop. Cool. Okay, so we can remove this. We are not using this stack anywhere. Instead of PID, we can call it now TID, which is more accurate. And we can even use this function to change the thread name when the function starts. I mean, it's so nice. Let me just see if this weight is correct. I guess I can simplify this a little bit. I will just make this atomic. And instead of passing those, we'll pass an assembler. Probably makes sense for us to wait here for this thread to start. Maybe atomic is not a good... Or maybe it is, who knows. Oh yeah, we want to do the C's here. So we need DTID. Whatever, I will just call load all the time, whenever I need it. Let's see if this still works. Suddenly created this monster. I could put it here maybe. Okay, now inside this thread things will happen, right? The assembly will execute and eventually the prolog function is going to return. Now this assembler should give us the return address. So here, for example, it should give us address of this jump. Let me run this. Okay, assembler returned this thingy here. I think, once we have this, I think we should subtract the machine code. And base address. Because the machine code can be loaded at all sorts of funky addresses like this one. We don't want the absolute value, we want the relative value. 40 in hexadecimal. So let's disassemble this and see what's at address 43. Nothing. Actually, no, when I look at this, is the loop instruction. Which should call here if it matches. Okay, so I think this is correct. It just gave us address right after this call, which is 43, correct. Nice. So if we tracked the exit points, those calls, each of those calls is an exit point. This will allow us to know where we exited the assembly world.
Marek Kowalski says,
Hey, how's the progress?
Actually nice. We have sort of an assembler already. So all of those instructions, we can execute them and they will work. We even have loops here. So here I can do something like that. So the array X register can be incremented. Maybe running this multiple times doesn't quite work. Oh, it's just like visual artifact. So each instruction is connected to some kind of owner object, and this is this owner object. And those connections should be invisible, so they should be implicit pretty much. We should hide them. Absolutely.
What's the red tape rope?
Okay, we managed to switch from clone to C++ threads. Reuse the same thread and stack. It's probably a good idea. I don't know.
There's some delay with TTS.
It depends. When I'm typing or speaking, it actually pauses. So I can actually see on my screen. Let me switch to Wally. Yeah. So when you're saying something, it waits until mic is gonna go silent. Usually just a couple of seconds, until I shut up. Maybe we can create some tasks so that it's clearer where we want to go. So we have assembler that can execute assembly code. The code can have loops. I think one task is to keep the assembler thread alive after machine code ends. Then when we have this getText function, okay, we are just checking registers, this regs value, this regs object. I see we are keeping track of it like that. I think we need another, it will probably be atomic. We'll think about thread safety later. Right now, let's just make it work. Yeah, I think starting a new thread can be slow, so it would be nice if the assembler thread would exist in the background. Okay, so when we want to print the text, instead of checking the value from this nice regs value, which is actually going to be incorrect when the thread is running, we kind of have to interrupt this is a very strange structure. This is just for debugging anyway, this function. If we are running, then we are going to call ptrace. Ptrace, how was this? Interrupt. Next, how do I get registers? I can also do this, pick user. Pick user is probably going to be easier. This user. It's called user, but it's not really related very much to the user. It's actually describes how Linux tracks user space programs. So for each user space program, Linux has this struct which contains values of every register when the thread is paused. And we are pausing it when we call ptrace interrupt. Okay, now this is something that should display a register even when the object is running. So for infinite loops. For infinite loops now we should have a very messy display which will just continuously show changing values. So let's create a loop. Let's run it. Oh, what's that? It's either 0 or 58. We definitely have our assembly thread running here. I just wonder why it oscillates between two values. Let's try again. Let's try with a larger register maybe. Let's grab larger. instruction, this one that increments 64-bit register. And let's run it. Nope, it just switches between 0 and this huge value. I guess it's time to read the documentation. Okay, that should just stop it. That should work. Andre is ignored. Nice. I can check the return status. None of this should happen really. Ptrace interrupt failed. Maybe it has to be a separate process, maybe it cannot be just a thread. I will try to bring back some of the functions. Okay, let's try bringing back this set dumpable. Is this going to change anything? I don't think so, but let's see. Nope, that doesn't seem to be enough. If this doesn't work, then maybe we should replace the JThread with clone and bring back our stack. I'm not a fan of clone because clone is a super complex function. We'll have to go through every argument, every option to make sure we are doing this properly. Nope. We are still failing with the interrupt. No such process. it would be nice if ptrace sees through those errors, not ptrace interrupt. No such process, come on. Oh yeah, I should recompile. After I disabled this writing, because I was writing TID into this variable, I think the way tracing works is I think it needs to work on processes so that multiple threads will be paused, yeah, if necessary. I mean, it still fails, so that's not great. I just want to see if I can call interrupt immediately here. Okay, it seems like now it worked. Again, it looks like it works. somehow. Now it's saying TID equals something, right? I'm logging this here. Is running should be set to true now. Apparently it's not. What is going on? So this ptrace interrupt failed is being printed here, but not in the console, not in the terminal. Now it's a little bit better. Maybe it's because I was running this under in my build system. Actually, go away. I will run this like that. ptrace getRegs failed. So interrupt worked. Okay, maybe getRegs failed because we finished execution. Simply. It was just too fast. If I understand correctly, right now we should have a busy loop. We don't. Okay. Okay, so we started the thread using clone. Now we are using clone again. And we printed this. ptrace sys worked. ptrace interrupt worked. And then we tried ptrace getRegs, which failed. And our loop, it doesn't seem to be running right now. I will just print thread started and assembler returned. When it finishes. And I want to see a loop, because I cannot get them to print real-time data. So this is our machine code, it's fine. Okay, we don't see any kind of results from other threads because probably because of my build scripts, but now we should see everything. So we say what the PID is currently, then we say thread started, so that thread is definitely starting, it crosses this line, and it never reaches this line. If I look here, it looks like the interrupt actually worked. So it seems that the assembler thread is paused after this interrupt. Then we'll call getRegs. And getRegs fails. No such process. Okay, so maybe when I call this interrupt, I should wait until it stops. Let's change this PID, and it doesn't have to be atomic. Traces does not stop the attached process. Okay, so this is the new way of tracing, which we are using actually, which should work nicely. Stop at tracy, so maybe it actually sends a signal to our new process, and that signal stops it. So we are cloning signal handlers. See the signal handler that we are kind of cloning. Okay, we are just setting everything up, so when whatever happens, we will call assembler signal handler. Makes sense? Okay, so here we are setting this SA on stack flag so that signals are handled on the stack, so that multiple threads don't mess with each other. If none of the above applies, this is the case we are in. For example, if the trace is running in user space, it stops with ptrace event stop. Okay, so maybe the signal that was actually delivered was none of those that we intercept here. Maybe it was seek trap. Let's see if we can intercept trapped. Okay, now everything locked up. I will disable the printing of machine code because it looks fine. It doesn't look wrong in any way. Oops. Okay, so hooking the trap actually caused us to just pause. It doesn't do anything when we are hooking trap. So this definitely does something. What it is though? Supposedly now we should have a actually I can do PS3. Okay, so our fish shell runs Python 3, which runs Python, which runs Automat, which runs 10 different Automat threads and an assembler thread. Okay, it's there, it's not stopped. I mean, it's not crashed. But it's also not running. So I think when we started this thread, the first interrupt worked. So I think maybe we should put some kind of wait pid here. Let's try this. Let's see what happened. So thread started, wait bit finished, and we managed to get the register. Okay, so the key was after we do ptrace interrupt, we should wait. Okay, let's try to duplicate this here in the text function. Because I think what could be happening is that or maybe it's not happening. So here we are printing TID. Yeah, we are printing TID. It seems like the first interrupt is already failing. Maybe this is the problem. Okay, this is suspicious. Why did we print it twice? What is going on? Look at that. There is TID colon 0. Okay, there is some multi-threading erasing going on here. But we are printing this TID. And we are getting no such process. Actually wonder, does this specific thread need to be attached? Right now, the assembly thread seems to be running at full speed. So I think there are multiple issues happening here. I want to eliminate one variable. I want to eliminate this wait PID. Let's create a loop. Yep, start it. Now it's running. I think maybe printf isn't super thread safe. Okay, I have a different idea. I'm not going to seize anything here. No pit tracing, no wait pit, getregs, no continuations, nothing. I'm just starting it so that it runs. Now it should totally fail, obviously. I mean, it will run, but we are not able to attach to it or read anything. It uses 100% of the CPU, so that's good. It means it's running. What I want to do is I want to do this seize here. And actually, instead of seize, I could even go a step further and do trace attach. Because I think because attach also stops it immediately. I will look into this. So now this attach, let's see if this works. didn't rebuild it, and that's the issue. Operation not permitted. Actually, something different happened. Peter is detached, no such process. Okay, so maybe after this so I shouldn't do continuation, interesting. Because apparently it has to be stopped for the detach to work. Again, I'm just trying everything. Eventually it's going to work. Look at that. It is working now. So whenever we refresh, we can see the current value of area X. It's usually a small value. Cool. Finally. Let's do a different incrementation. Maybe something that increments 64 bits. And let's run it in a loop. Pure virtual method called what? Okay, 16-bit value increments nicely. (32-bit value). Yeah, for this one, in the highest nibble, we can actually see it incrementing. The lowest ones are so fast that it's hard to see, but this one is actually counting. You see, it goes from 1 to 10 and A to F. Why did 64-bit fail? Did I do something differently? No, it is working. Cool. It will actually take a very, very long time until I roll over 64 value increment. But there we have it. So it is a thread which is running at full speed because I'm only rendering it like when I need to. See, when I move around, I don't change anything. Probably I should invalidate it. I should mark it as animated. But yeah, it essentially allows the thread to run uninterrupted. So we have full speed assembly execution in a dedicated thread. Okay, multi-thread debugging is messed up. Concurrency story for this code is going to be crazy. It's crazy, but I think it should be possible to roll over this value. If we run this in multiple threads multiple threads would not work. It doesn't matter. Okay, when it comes to displaying this stuff on screen, I think a different architecture would be probably better. I think we could have a single tracer, and that single tracer should probably be not the UI thread. Because here we have UI thread which temporarily attaches to the assembly thread for a single frame, reads registers and says goodbye. I think a better architecture would be to have one of our threads be this dedicated thread that talks with the other one. I could even do different things. Let's see the randomize, for instance. I'm curious how it would work. Let's just run it. Let's see how it works. Yep, it's a random value, definitely. Okay, the second failed because we have this long-running object that we have to fix. Let's get rid of this set dumpable. I don't think we need it really. Yeah, still works nicely without it. I'm not 100% sure, but I think Linux will not be happy if we try to attach to these ptraces from multiple threads. Yep, there is just one tracer. Actually, now that we managed to clean this stuff, maybe it's possible to switch to C++ threads. Right, I can run this. So we are getting a separate thread which kind of rolls over this counter. So let's see. Okay, and then now we need to set this PID again. It would be nice to not worry about thread. Seize failed, operation not permitted. don't know. We could try this PRCTL-set tracer. Maybe that would work. Okay, I'm afraid we are not going to use C++ threads after all. I mean, so honestly, clone gives us, it's more complex, yeah, but it kind of gives us better control. So it's not that bad. Okay, let's leave some to-dos about stuff that we can do. So we're using the same thread. Absolutely, we should do that. Those are basically the same. The idea here is that once we do this clone, this thread should really live as long as the assembler object, and it should probably exchange messages through some kind of message passing system. I think we, in the end, may have two threads. There will be traced threads and the tracer, which is going to be permanently attached. Because I think constant like seizing and unseizing, this kind of stuff, we're probably like moving some pieces of the kernel which we shouldn't have to move all the time. It's probably not a great idea to constantly, detach and attach on every frame. On the other hand, interrupt and continue, those could be better. So the way that threads will work is that we will have, I will use, I don't know, this for threads. We will have asm thread. This is the worker. This is the one that's going to do the actual work. And then we will have tracer. And they are going to talk over ptrace interface. And they are going to be owned by So I'm back. So we will have this tracer, which is going to be, let's draw it like that. Vertical alignment, let's top. And this tracer is going to be a multi-threaded object. That is going to talk with, so it is kind of going to own the, sorry, tracer, assembler. That is going to talk with the tracer thread over message queue. So that, for instance, when we are rendering, right, we want to render fast. We don't want to have any wait PIDs on the rendering path. That would be really bad. So the way we will do this is that we will just send requests. If we are animating, we will just send requests. Hey, give me the current, I know, register state. When a frame renders, and we will take maybe not the most recent state of registers, but the one from maybe previous frame, something like that. Some kind of lazy operation. We will basically decouple the rendering from this wait PID, and we will decouple rendering from tracer. Yeah. So a UI thread will communicate with tracer over this message queue and with assembler. Okay, so this is how I see the thread situation, at least after those quick experiments right now. We may be able to squeeze a little bit more interesting things if we read documentation for the clone syscall. There are just tons of options here. This is a massive syscall. As you can see, there are plenty of very weird options here. And there are a bunch of options related to tracing. There is also a chance that we could use C++ threads, because the issue that I had here, it was a permission issue, and it was clear that there is a way that this permission could be resolved somehow. For instance, if we use this architecture, right, the tracer is going to be the process which creates the assembly thread. So it is going to have a permission to trace it. Okay, so this is how the assembler could work. And this operation with two threads can actually be optimized by, I think the threads can be eliminated essentially. We could just jump into the right address directly without any thread shenanigans. Okay, so we should definitely introduce this architecture for threads. This is what we should do, that's the plan. Then we should hide the connections. It's nice that they are there, but they should not. Then we could be more clever when we emit instructions, so that we should put, right now when we have a sequence of instructions with a jump to the start at the end, we can start emitting them from the middle, which is not a good idea. We should start emitting them always from the front. So head instructions should go first. Then we have this option with terminators. So we should not emit exit points after instructions which kind of terminate a basic block. Then we should identify the instruction that finished, or like the last instruction. So identify the exit point. And continue automatic execution from there. There is that. There is also this idea of long running, so we should probably so when we set long running, so as the assembly executes, we could continuously update. Like for each instruction, we could clear the long running and set the long running on another one. That's one option. But the instructions are super fast; they execute like instantly, so it's not going to be very usable. So I think maybe when assembler starts, we could update all of the instructions and set all of them to long running, because this means that kind of our assembler runs. If there is a block of machine code that executes for a long time, we have to somehow keep track of this, allow the user to cancel this execution, or maybe start multiple. I mean, it should be possible to start multiple of them in parallel. All right. And I think with the start we currently have, we can also start making the widget. The key thing that we have is, I mean, we have access to these user regs, so we have everything really. This stuff, it's absolutely crazy what we have here. Basically all of the general purpose registers. I have no idea what are those. What is magic, ucom, fp state word? Cool. So this is the plan for our assembler. Those pictures, I think we can delete them. Kind of know we kind of have this working already. Okay, so that's it for today. See you on Wednesday when we will try to start this widget work, because those things, I mean, they are annoying. Yeah, probably this we should do. Everything else is, I mean, it's terrible that we have this, but it doesn't stop us from working on the widget. So on the next stream, we are working on the assembler widget. Okay, see you then. Bye.